In this video, I want to take a look at Abel's theorem, which tells us about the Wronskian of solutions to second-order homogeneous equations. Now, I should point out this is second-order homogeneous, not necessarily constant coefficients. That I'm going to be looking at a differential equation of this sort, where the p of t and the q of t in here. We've been working with constant coefficients, but this theorem is a little more general. So if y1 and y2 are solutions to this second-order homogeneous equation, then Abel tells us that the Wronskian of y1 and y2 can be calculated as a constant times e to the negative integral of p of t dt. That only depends on this right here. And that c depends potentially on y1 and y2, but it doesn't depend on anything else. Something to note here, that the Wronskian of y1 and y2 is either always 0 if c is 0. For instance, if y1 and y2 are linearly dependent, then the Wronskian should be 0, and that would happen with c equal to 0 here. Or this is never 0, because the exponential would never be 0, and if c is not 0, then the whole thing's never going to be 0. So that's not to say that you can't have functions having a Wronskian that is sometimes 0 and sometimes not. We saw that in the example, one of the examples I gave on the previous video. But what that tells me is that that pair of functions, I think it was x squared and x I did, and it got a Wronskian of negative x squared, which was sometimes 0, but not always. So that tells me that those two functions cannot both be solutions to the same homogeneous linear differential equation here. They might individually be solutions to differential equations, but they won't both at the same time be to the same one, right? Because their Wronskian was sometimes 0. Now, let's prove this. It actually is a fairly straightforward proof. So here we go. If y1 is a solution to that differential equation, then plugging it in gives us this true statement. Likewise, y2 being a solution would give us a similar statement. Now, what I'm going to do is I'm going to multiply this top equation by negative y2, and I'm going to multiply the bottom equation by y1. So you'll see there's a negative y2 that gets multiplied in everywhere here. It also gets multiplied over here. Don't forget to multiply it on that side. And likewise here, the y1 gets multiplied by everything. So there's a y1 there, and a y1 there, and a y1 here. What that accomplished was that these two terms here now look the same, one with a plus, one with a minus. So when I add those two equations, those two terms are going to go away. So that's what I want to do next, is add those two equations. So here's the y1, y2 prime, minus the y1 prime y2, so that was this one and that one. And then there's two that have a p of t in it, and I factored that p of t out. So you got a y1, y2 prime here, and then a minus y1 prime y2 there. Okay, and of course the 0 plus 0 is 0. I put a little star right here at the end of this because I'm going to reference back to this equation later. At the moment, I'm going to take a look at something here. I'm going to let w equal the stuff inside parentheses here. And my attempt is going to be to turn this into a first-order linear equation that I can solve. Okay. So, first-order linear differential equation that I can solve. So let y be this. And if you look in the textbook in their proof, they just say, oh, let y be this, so let w be this, so w prime will be, and they just give the answer, and it's like, wait, that's not the way you do that derivative. So I'm going to do it out here. If w is this, which is y1 and y2 are both functions of t, so this is one big old function of t. But there's a couple of product rules in here in order to take this derivative. So on this first product, there's y1, y2 double prime, but then there's a y1 prime, y2. So first times derivative of the second, plus the second times derivative of the first. And then I'm going to subtract the product of this thing, which is, again, a product rule. So there's a y1 prime, y2. So first times derivative of the second, plus the second times derivative of the first. So there's a y1 double prime, y2 for that. But that's being subtracted. Notice that the y1 prime, y2 prime is a negative here, but it's a positive there. So those go away. And the net result is you get y1, y2 double prime minus y2 double prime. Sorry, y1 double prime, y2. The derivative of this thing is that thing. It's really odd because it looks like the y1 just acted like a constant and the y2 here just acted like a constant. But that's not what happened. It just things canceled out along the way there. So plugging this back in, this stuff in parentheses was the w, and so there's the w times p of t. But this stuff over here was w prime, so this is w prime. This turns out is now a first-order linear or separable differential equation, and I can solve those. I think I'm going to choose to do it separably. So first of all, I'm going to subtract this over to the other side, then divide both sides by w and multiply both sides by dt. This w prime is the derivative of w with respect to the variable involved here, so dw dt. Hence the dt there. And so then I integrate both sides, and the integral of 1 over w dw would be the natural log of the absolute value of w. We've done this many times already, right? And you integrate this side, you get whatever it is. I don't know what p is, but if I knew, I'd integrate it with a minus sign there. Then exponentiate to solve for w. And remember about the plus c, that turns the e to the c into just a c, but that's a positive or negative constant. And when I get rid of the absolute values. So there it is. The Wronskian is equal to, because w, by the way, sorry, I said let w be the stuff inside parentheses. What I failed to mention is that w is actually the Wronskian of y1 and y2, right? This is what you would get if you took the Wronskian of y1 and y2. So, yeah, so it wasn't by accident that I chose w here as my my letter. So the Wronskian is constant times e to the minus integral of p of t dt. Let's take a look at a couple of examples. One example. This equation right here we solved in a previous video. The Abels Theorem here tells us that the Wronskian of any two solutions would be a constant times e to the minus integral of 3 dt. The p here is just a 3. So that would be c e to the minus 3t. Now what we found when we solved this, we found two independent solutions. We found e to the negative 5t and e to the 2t, right? Because the characteristic equation here was r squared plus 3r minus 10, which factored into an r plus 5 and an r minus 2. And so these were the two solutions we found. And if I look at the Wronskian of those two, I get determinant of this thing, which is, what's this, 2e to the negative 3t minus negative 5, hence the plus 5e to the negative 3t, which is 3e to the minus 3t. So the Wronskian of those two solutions was 3e to the minus 3t. If I'd chosen a different pair of solutions, for instance, we noticed because this is homogeneous, once you have one solution, you can just multiply it by a constant, get another solution. So if I used e to the minus 5t and let's say 7e to the 2t, there would be a 7 here, and there would be an extra factor of 7 there, which means there would be an extra factor of 7 in both of these, and the answer would just be 21 e to the minus 3t. So the constant out front changed because I chose a different pair, but still, it's just a constant times e to the minus 3t, either way you look at it. Okay. So there's Abels Theorem. We will use this mainly to help us find solutions. When we have one solution but we don't have two, this will actually help us find a second solution, as we'll see in not the next section but the one after that.